Hello, my name is Dennis Cabrera Garcia, and today I will present to you the work entitled Cross-Linked Polymer Thin Films for Boron-Gate Transistors in Sensing Applications. This work is a collaboration between the Molecular Electronics Group of the University of São Paulo and the University for Latin-American Integration. Cross-linked polymer films were investigated to fabricate boron-gate, boron-contact, organic thin-film transistor-based sensors in order to detect gaseous sunlight. In the presence of the gas flowing through the semiconductor containing the gaseous sunlight, it should produce changes in the electric current flowing between source and drain. The device structure and the chemical structure of organic molecules are presented in these figures. PVP and PMMA molecules were cross-linked with PMF molecules at different ratios. Metal film for capacitors were 5 nm thick nickel-chromium adhesion layer, followed by 95 nm thick gold layer by DC sputtering. Electrodes were patterned over glass substrate by photolithography, followed by etching. Photomasks for patterning both bottom and top capacitor electrodes are shown in the following figures. It has 32 capacitors whose areas are defined by the overlapping of squares with size of 25, 50, 100 and 200 micrometers. In this slide, we can see the sequence of steps to fabricate organic capacitors. Note that in order to obtain functional devices, it was necessary for the dielectric polymer to resist photolithographic processes to pattern the electrodes. In the absence of cross-linking, photolithography of electrodes tends to damage the dielectric film. On the other hand, a higher cross-linking density generates a more defective and consequently porous film. Although a higher surface area is desirable for gas sensing applications, if the leakage current gets too high, an additional insulating layer may be necessary for proper transistor operation. Thin films of organic dielectric were studied by using Fourier transform infrared spectroscopy and atomic force microscopy. Also, the organic dielectric resistance was studied, analyzing the thickness variation as a function of O2 plasma etching. Electric devices such as capacitors had the current versus voltage and capacitance versus voltage curves extracted by keysight instrument in a micromanipulator. Now we discuss the results of thin films thickness variation as a function of O2 plasma etching time. Note that thinner films have less data points since they get fully etched after a shorter time compared to thicker ones. Among films without the cross-linking agent, PVP has a lower etching rate compared to PMMA. By adding PMF to PVP at 1:1 mass ratio, there is a decrease of approximately 28% of the etching rate. Further increasing PMF ratio doesn't alter the etching rate. At this ratio, PMMA with PMF showed the highest resistance to O2 plasma etching. Even though cross-linked films are harder to etch and consequently to open bias in integrated circuits, these results corroborate the presence of cross-linking already at 1:1 ratio. These results of atomic force microscopy demonstrate that the surface roughness of PVP with PMF films are not severely altered by a cross-linking process, since the results found in the literature for PVP films without cross-linking slightly change. In addition, these root mean square roughness values are adequate for application in OTFTs, while PMMA with PMF at the same ratio featured a root mean square roughness at 6.8 nanometers. A rougher film could be originating from a lower spinning frequency. Higher rotating speeds are biased to OTFTs, since semiconducting film thickness can be even lower than 20 nanometers. In this slide, let's see the results of thin films characterization by FTIR spectroscopy. The molecule of PVP is composed by the hydroxyl group, which has a strong presence without cross-linking with PMF. That can be seen in this graph. Once the molecule of PMF is added at 1:5 ratio, then the hydroxyl group bands tend to decrease, and in some cases disappear, which indicates that the cross-linking occurs. Similar results can be observed for PMMA films. In the FTIR spectrum of PMMA without PMF, a strong presence of COCH3 bands can be seen. We can affirm that the cross-linking between PMMA and PMF exists when these COCH3 bands decrease when PMF is added. In the opposite trend, there was an increase in bands related to the triazine ring attributed to CN groups directly attached to it. After the thin film characterization was made, some capacitors were fabricated. Devices of PVP and PMMA without cross-linking didn't work. Therefore, they didn't withstand the lithography process. The table summarizes the electrical performance of capacitors from cross-linked organic dielectric films. Besides, we can observe that devices with a higher PMF ratio had not only higher dielectric constant, but also higher leakage currents, which are a sign of enhanced cross-linking. However, this current was more uniform compared to devices with less PMF, and the breakdown voltage was also higher in this case. It is worth noting that a decrease in the concentration of hydroxy groups in cross-linked PVP, as shown in FTIR spectrum, is also beneficial to diminish charge trapping at the dielectric semiconductor interface in OTFTs. Previous reports on cross-linked PMMA with different cross-link agents featured a K of 3.7 to 3.9, which agrees well with the dielectric constant obtained for PMMA with PMF devices at 1:5 ratio. In addition, PMMA with PMF films seem not to completely withstand damage from the photolithographic process because they feature a large dissipation data among capacitors. Okay, so now the final conclusions. Cross-linking of both polymers was verified from chemical resistance assays and structural characterization. Photopatterned high-K capacitors from both blends were demonstrated. It was the first demonstration of device feasibility from PMMA with PMF films. Despite that, PVP-based films were considered more adequate to integrate boron-gate boron contact organic transistors. Chemically resistant organic dielectric films will make possible flexible, transparent, integrated circuit-based and potential low-cost sensor with fully photopatterned electrodes. Well, this is the end of the presentation. Thank you so much for your attention today. If you want to ask any question, feel free to do it.